Today we're going to talk about optimization, which is more word problems, right? It's still going to be a lot of taking something, some words, and interpreting what that means mathematically. So it's a lot of kind of taking what's written and being like, okay, well, what does that really mean? So I guess we could also read the words written down. Optimization problems are word problems, like I said. Sometimes real life problems, sometimes totally made up problems that are supposed to be quote unquote real life, where we try to get the best of a given situation. The optimal solution may be the maximum or the minimum, depending on the context of the problem. So just to kind of think about that for a second, if we're going to be trying to find where these things are maximized or minimized, most of the time, at least in this class, that's going to mean we're going to be looking for some portion of the vertex of a parabola. Because at this point, those are really the only kinds of functions we know how to find the maximum or the minimum of. Next quarter, or the quarter after that, when you start taking calculus and learning about derivatives, you will learn how to find maximums and minimums of really any kind of function. But at this point, really parabolas are what we're kind of limited to. So what you're going to often see is whatever kind of situation we're in, eventually we're going to be able to write some function, and it's usually going to be a quadratic. And then we're going to try and find out what the maximum or minimum of that is by finding what its vertex value is. So just keep that in the back of your mind as we move forward. So let's look at this example. Also, for the people on Zoom, here's the things as usual. You need a pen, I suppose. Dumb bag of pens here. Okay. All right. So come on in, grab some notes. Grab the notes. Grab the notes. Okay. So we're talking about optimization. And in the side here, I will try to write not too terribly the kind of general guidelines for what we do when we're optimizing the problem, optimizing the situation. And the first thing we typically do, if it is warranted, is to draw a picture. Sometimes drawing a picture doesn't really make sense because like you're given just a situation that doesn't really lend itself well to drawing a picture. But if you can, draw a picture. So let's see, let's read the question. Maybe that should be the really first step. Read the question is the real first step, then draw a picture. So let's see what we've got here. A farmer has 120 feet of fence to build a rectangular corral for his animals. All right. To keep the horses and cows separate, because of course farmers want to keep the horses and cows separate, the farmer needs a dividing fence. What dimensions are going to maximize the area for the corral? All right, so what I took away from that when I read it was, I've got a rectangle, a rectangular corral, and I need a dividing fence to keep the cows and horses separate. So I'm going to draw myself a rectangle. With a dividing fence. Now, you could really orient the dividing fence either way you want. You can make it horizontal, you can make it vertical. It doesn't really matter. I should say, I mean, I guess really you could make it diagonal if you wanted to, but I should have been more specific that it needs to be like a vertical or horizontal. It's going to split it right in half and not in a diagonal way, because that would be atypical, right? It'd be kind of weird. So let's, I guess I'll do it vertically like this. Great. So there's our corral. It is rectangular. And now we want to label the unknown things with variables. Because we're being asked here, what dimensions would maximize the area for the corral? Which means we don't know what the dimensions are. So if there's something that we don't know what it is, we typically want to give it a variable name. And I'm going to use slightly, let's go ahead and use slightly. I'm going to call this side here the width, and this side here the length. You can use X and Y, you can use A and B, whatever you like. And I guess I could label all the other things too. So technically, this side up here is also the length. This side here is also the width. This side here is also the width. This is not the only way to do this. Come on, no, you're good. Come on in. Some people like to call like this part here, like half of this, like the Y value or the whatever. That also works out just fine. This means you have to interpret your results a little bit differently, but kind of any labeling that works for you will work. I should say you want to use the least number of variables possible, meaning I shouldn't call this W and this X and this Y because they're all the same. I shouldn't call this A and this B because they're the same. I should say the things that are the same should get the same variable name. Okay, so now step 2. We want to write an equation for the thing that we are trying to either maximize or minimize. In this problem, we are trying to maximize the area of the corral. So I want to write an equation for the thing I'm trying to optimize. So in this case, that's the area. And the area of a rectangle, pretty straightforward. The area of a rectangle is just the length times the width, or the base times the height, or the one dimension times the other dimension. That's your area of a rectangle. Okay, so here's the thing. This function is a function of 2 variables, right? We have length and width. And the problem is we really want it to look like a function of 1 variable. We really want it to look like a function of 1 variable that looks like a parabola, because we know how to maximize or minimize a parabola. So what we need to do is then find the constraint. There is usually with these problems some sort of constraining piece of information that's limiting how much we can build. Right? I can't build the biggest corral I want. I can't build a corral that's 80 feet that way and 20 feet that way because I don't have that much fence. Because 80, 20, 80, 20, and 20, I only have 120 feet. That's way more than 120 feet. So I'm limited by how much material I have. So we have to then find an equation for the constraint, if there is one. So in this case, we're constrained by how much material we have to build our corral with. And our constraint's going to look like, well, all of these sides, all 5 of them have to add up to 120. I guess you could add to less than 120. Since I'm trying to make the biggest corral possible, I'm going to use all of the fence. So I'm going to use all of the 120 feet like that. So I want my W plus W plus W plus L plus L, W plus W plus W plus L to equal 120. Or more succinctly written, 3W plus 2L should equal 120. That's my constraint. And then what we're going to do, so something to kind of take note of when you're doing problems like this is the thing you want to optimize is never going to equal a number. It's going to be something, and then we're going to try to find out what maximizes it. On the other hand, the constraint is usually going to be equal to some number because you are limited in how much material or space or whatever you have. Then we're going to solve the constraint for one of your variables. Solve the constraint equation for a variable. Sometimes the choice is obvious. Sometimes the choice is not. In this problem, either choice is fine. You could take your constraint equation and isolate L. You could take your constraint equation and isolate W. Either way will work out. I don't have a particular, right? I don't see a better choice here, right? Either way, I'm going to have to get a fraction in some way, shape, or form. So it doesn't really matter which one I choose. So let's go ahead and pick, I don't know, let's pick L. So I have 2L equal to 120 minus 3W. And if I divide everything by 2, I have L equal to 120 divided by 2 is 60. And negative 3 divided by 2 is just negative 3/2. That's kind of all I can do with that. But now I've isolated one of my variables. If you, on the other hand, decided to isolate W, that would work out just fine as well. Sometimes one choice is like way easier though, so we pick that one on purpose. But if they both seem the same amount of terrible, it doesn't really matter. All right, step 5. Substitute in the isolated value to the thing you want to optimize. And see, my writing is not the best. So I'm going to take this L equal to 60 minus 3 halves W and plug that in for the L in the area equation. So I'm going to get the area is equal to L, which is now 60 minus 3 halves W times W. And now we have something that is a parabola, or it has a graph that's a quadratic, whatever you want to say. If we multiply this out, let's take a look. So yeah, let's simplify this a little bit. So we have that area is equal to, if I distribute the W here, 60W minus 3 halves W squared. And I suppose if you want to write this in the more standard way, area is equal to negative 3 halves W squared plus 60W. See that all right. I know my writing just okay. So there's a which way opening parabola. A parabola open upwards or downwards. Right, which means it's going to have a maximum, which is good because the question asks us to find the maximum. Right, so if you're being asked to find a maximum and you end up getting an upward opening parabola, something went wrong. Either the person asking you the question wasn't paying attention, or you might have made a mistake figuring out what the parabola is. So just be aware, right? If you're being asked for a maximum, you should find a maximum. If you're being asked for a minimum, you should find a minimum. No one's trying to ask you tricky questions that don't have answers. At least not yet. Not really ever in this class. I'm not a trickster. I don't try to be like, oh, here's them. No, I'm not trying to fool you. All right, so then we're going to find the vertex, because that's how we find the maximum or minimum value of a parabola. So we're going to, I'm going to say, find the appropriate coordinates of the vertex. So I'm going to go to my usual way of finding the vertex of a parabola. So I'm not going to say X here because I don't actually have X. I have W. I'm going to say the W coordinate, or the input coordinate, my V sub W. That's like the first coordinate of the parabola. And that's what's going in, is going to be my negative B over 2A, which in this case is going to be negative 60. That's my B value, 60, over 2 times negative 3 halves is my A value. That's going to work out all right. 2 times negative 3 halves is negative 3. And negative 60 over negative 3 is positive 20. All right. So that is the W coordinate of this situation, meaning that is what the width should be. That width value will maximize the area. Do I need to find the other coordinate of this parabola, of this vertex of this parabola? Maybe. It depends. What did the question ask us to find? So in this question, we've been asked to find what dimensions would maximize the area for the parabola. So I found W, right? This is, the width is going to be 20 feet. What else do I still need to find? Right, the length. Do I need to find the area? No, I don't. I could find the area. It's totally fine to find the area, but I don't actually have to find the area. So if I want to find the length, I'm not going to go back, or I'm not going to find the other coordinate of the vertex. I will in a second, just to kind of close that loop. But what I really want to do is just say, well, I know that my length is equal to 60 minus 3 halves W. So if I'm trying to find the length and I know the width, I can say that the length is going to be 60 minus 3 halves times 20. 3 halves times 20 is 30. So the length is going to be 60 minus 30, which is just 30. So the length is equal to 30 feet. So I don't have quite enough room here because I forgot I was going to write in here, but I would say step 7 is make sure you've answered the question. Make sure the question is actually getting answered. what I really mean by this is after you found this x coordinate of the vertex, go back and ask yourself, what am I actually trying to find? Am I trying to find the dimensions or am I trying to find the area? Because sometimes they'll ask different questions. So I could have totally asked the same question, except instead of saying, find the dimensions that maximize the area, I could have said, what is the maximum area? And then our answer would have been, well, since we know that the length is 60, right, the length is 30 and the width is 20, the maximum area would have been 20 times 30, which is 600. Now, never enough room. I just want to point out, since it's not what we're being asked here, but we totally could find it. If I did find the other coordinate of the vertex, so I know that my VW is 20. I know that my parabola is A equal to -3/2 W squared plus 60 times W. That's just my parabola equation. If I plug in that 20, I'm going to find the second coordinate of my vertex. So if I do that, I'm going to get -3/2 times 20 squared plus 60 times 20. Check this out. We get -3/2 times 400. 60 times 20 is 1200. -3/2 times 400 is -3 times 200, which is -600, which gives you 600. So here's what I want you to see, because this is important. When you're finding this vertex of the parabola, the first coordinate, the quote unquote x coordinate, or in this problem, the w coordinate, just tells you what value that first dimension is. It's telling us that w, the width, should be 20 feet. The second coordinate doesn't tell you the other dimension. The second coordinate of the vertex tells you the maximum or minimum value of the thing you're trying to maximize. So this second coordinate here, right? If I actually draw this parabola, might as well. Can I draw it? I mean, yes, I can. Let's see here. Okay, sure. This parabola looks something like this. And when we're graphing this parabola, oops, you can't see it. Oh, whatever. Sorry. Parabola looks something like this. Okay. A equal to -3/2 W squared plus 60W. The x-axis, or the w-axis, is our input, and the output axis is A. And this coordinate here is when W is 20 feet and the area is 600 feet squared. So that vertex is always giving you the value you need for whichever dimension you've written your function in terms of, right? We decided to write our area in terms of the width. So we found the width coordinate, or the width value. It's going to maximize the area. And the y value, or the second value of the vertex, is always going to be that maximized or minimized value. So sometimes they'll ask for that, and sometimes they won't. So a lot of these questions, it's really important that we read them carefully. That we be like, am I looking for the dimensions, or am I looking for the maximum or the minimum value? And there's definitely a couple questions on the next homework assignment where one of them asks you to find the dimensions that maximize the rectangle, and one of them asks you to find the maximum area of the rectangle. So just be aware that sometimes people ask for different things. Questions so far? Yeah. Sure. So on the x-axis, so I'm just pointing out, so I didn't do all the things I would normally do if I was drawing a parabola. So if I was finding all the things, I would say that's the x-intercept of 0. This is another x-intercept of 40. But the point I was really interested in was the fact that this vertex has a w coordinate of 20 and an area coordinate of 600. Because if I'm thinking about this parabola, I'm writing area in terms of the width. So if the width is 0, what's the area? If I have a 0 width corral by a however long corral, the area's got to be 0, right? And also, if my width is 40, we look back over here for a second. If I use 40 feet here and 40 feet here and 40 feet here, I've used up all the feet. 40 times 3 is 120. So if I had a 40 width corral, my length would be 0. So my area would also be 0. So all the points on this parabola are telling you a width coordinate and an area that goes with it. So for example, just to pick a number out of the blue, if I said the width was 10 feet, I'd have something that looked like this. 10, 10, 10. I still have 90 feet left to use for the other side. So this is going to be a 45 and a 45. That adds up to 120. And the area would be, well, I could either plug in 10 to my parabola and get that the area is -3/2 times 10 squared plus 60 times 10, which is -150 plus 600, which is 450. We can also see it from the picture here, because the area of this rectangle is definitely 10 times 45, which is 450. So this parabola tells you two things. It tells you the input is your width and the output is your area. But what it doesn't tell you is what the length is, right? Which is what the question asked for. The question asked for the width and the length. So I'm just trying to emphasize here that when you're looking at this vertex, the input coordinate is one of your dimensions, and your output coordinate is the maximum or minimum, if it's an upward opening parabola, of your function. But it's not giving you the other dimension. Okay. Let's look at a couple more examples. And the next example, of course, doesn't have all of these. Also, apologies for the quality of the copies. I accidentally made a two-sided copy when I printed it out, and when I did two-sided to two-sided in the copy machine, it got a little less than excellent. So I'll be sure not to do that in the future. Again, apologies for the quality is not excellent there. Let's look at this next question. So what have we got here? The company has determined that its total revenue in dollars for producing a product can be modeled by revenue equal to -x squared plus 450x plus 52,000, where x is the number of units produced and sold, and revenue is in dollars. What production level would yield the maximum revenue, and what is the maximum revenue? Okay, so this problem doesn't really have any of the features that the previous one did, which is kind of unfortunate. Right, we don't have a constraint. We're already kind of being told what the function is that we want to maximize. So we're being asked to find out what value of x maximizes this function, r equal to -x squared plus 450x plus 52,000. Make sure I'm not skipping anything important here. There isn't a constraint, right? We don't have any second piece of information. We already have the function we need, and it's in terms of a single variable, so we're good to go. Sometimes we're lucky that way. All right, so we've got a downward opening parabola. We want to find the value of x that's going to maximize it. We're trying to find the x coordinate of the vertex. So we want to find v sub x, which in this case is going to be, well, it's always going to be negative b over 2a. In this particular case, that's a negative 450 over 2 times -1, which ends up being 225. 225 watts? Units, I guess, right? X is the number of units produced. So a value of 225 units. So what we can say so far is producing 225 units will maximize the revenue. It's not telling us what maximum revenue is, but it is telling us that if that's our value that we plug in, that will give us the maximum revenue value. We're also being asked to find the maximum revenue value, so we are going to plug in. It's not going to be pretty. We're going to plug in 225 to this less than nice parabola, right? The numbers are kind of big, but we can handle it. So let's see here. If I want to find the maximum value, I'm finding the second coordinate of the vertex. I usually like to use the letter name of the function. So you could say this is y equal to negative x squared plus 450x plus 52,000. I've said r because that's what they told me to say. So I'm going to say that the second coordinate of the vertex is v sub r, but it'd be fine to write v sub y. And I'm going to find it by plugging in x equal to 225. Because again, right, what I'm doing is I'm just finding that point on the vertex of the parabola. The x coordinate is 225, and the revenue coordinate is what I'm about to find by plugging it in. And it's not going to be, I mean, I would use a calculator here. I've already got it written down, so I'm not going to pull out a calculator, but I definitely use the calculator to calculate this. It's going to be negative 225 squared plus 450 times 225 plus 52,000. Let's see, that ends up being negative, let's see, 225 squared is 50,625. 450 times 225 is 101,250. And then if we add this all together, we end up getting $102,625. And that is the maximum revenue. And I really, really want to stress it's the maximum, right? You could plug in any other value for x. Right? You can say like x is 200 units or x is 300 units. And if you plug that in and you calculate the revenue at those different x values, you'll get a lesser revenue because this is the top of the parabola. Right? There is no other x value that's going to produce a higher output revenue value. So a lot of these questions are going to, so the hard part usually for these questions is not finding the coordinates. The hard part is usually the setup. Right? Finding the vertex is a relatively straightforward process. You do negative b over 2a to find the input, and then you plug that in to find the output. The harder part, and not for this problem so much, but the harder part for other problems is the setup. It's figuring out how do we find the right parabola to even write. So let's look at the next one. On track here. Yes, the next one. That's a good one. I like this one. There's definitely a couple problems like this on the next homework assignment. This is the one I was actually talking about, where one of them asks you to find the dimensions of the thing, and the other one asks you to find the maximum area. So when I read this question, I want to kind of start thinking about what I'm doing. So it's saying find the dimensions. Okay, I'm looking for the dimensions. No one's asking me to find a maximum value or minimum value. I'm just trying to find the input. Find the dimensions of the largest rectangle by area in the first quadrant that can be inscribed under the line y equals 18 minus 6. Okay, I should definitely draw a picture here. I definitely should draw the line y equals 18 minus 6x. To draw the lines, I should think about the intercepts. Oh, geez. It leaned against the button. I didn't even touch it with my hand this time. It's terrifying. Okay. So for this line, let's talk about the line. So y equals 18 minus 6x. The y-intercept is going to be, well, if x is 0, y is going to be 18 minus 0. And the x-intercept, if y is 0, I've got 0 equal to 18 minus 6x. If 6x equals 18, then x equals 18 divided by 6, which is 3. So those are the intercepts of my line. Draw it the best I can. Something like this. Notice I drew the line before I labeled my intercepts. I highly recommend doing it that way because then then you don't miss. Also, this is clearly not to scale, right? My y value would be much, much higher, but I want to draw it in a way so that I can actually draw the thing relatively well. So now I want to find the dimensions of the largest rectangle in the first quadrant that can be inscribed under this line. So it can't, so if you're thinking about the XY coordinate system, right? This is quadrant 1, this is quadrant 2, quadrant 3, quadrant 4. So we want to be only in quadrant 1. We want to be inscribed under the line, meaning we can't go over the line. So I can't be like this. I have to be kind of like that. There's my rectangle. But it could have been, right? I didn't have to draw that rectangle. Maybe it was going to look more like this. Right? I don't actually know what my rectangle looks like. And when I don't know what the actual dimensions of things are, that's when we give them variable names. So after we've drawn our picture here, we should label, let's see, I'm going to label this side of the rectangle X and this side of the rectangle Y. Great, we've drawn a picture, we've labeled the things we don't know. We want to find the dimension of the largest rectangle. So that really means we want to maximize or minimize. Maximize. What are we trying to maximize? The area. We're trying to find the dimensions, but we're trying to maximize the area. So we're definitely maximizing the area of the rectangle. And to do that, we need an equation of the thing we're trying to maximize. So we know that the area of this rectangle is X times Y. Base times height, length times width, whatever you want to say. And just like in the first problem we were looking at, I have the thing I want to maximize as a function of more than one variable. I don't want that. And that's going to be true also when you take calculus. You're going to have problems, you're going to have optimization problems in like chapter 3 or 4 of calculus, or depending on which calculus you take. Where you're going to have a function and it's going to have two variables and you're going to have to do the same kind of thing. It's going to be a more complicated function. So we need a constraint. So in this situation, we are constrained by the fact that this upper right-hand corner of the rectangle needs to be on or below this line. Now, below wouldn't give us the most area, right? I wouldn't, if I'm trying to get the most area, I'm going to make that rectangle as high as I can, or as far right as I can. I'm not going to stop, you know, like if I was, again, back to this other picture, I'm not going to draw like this rectangle here where I haven't used up all of the possible space I can. Right? I would extend that either upwards or rightwards or both. So I definitely am constrained by the fact that this upper right-hand point of the rectangle should be on that line. Oh, but I know the equation of that line. So this point here, which is the point X comma Y, because I've gone over X and up Y, the constraint for that point is that Y better equal 18 minus 6X. That is our constraint. That point has to be on that line. Well, great. It's already solved for me, right? I've already isolated the variable. I've got Y by itself. So I'm going to take that and substitute that in right there. Substitute in. Substitute. I can spell. Not the spelling is important. Misspell a word, not a big deal. And we're going to get the area is equal to X times 18 minus 6X. And if you want, and I kind of do want, I'm actually going to write A of X to really emphasize the fact that the area is a function of X. And if I multiply this out, I get 18X minus 6X squared. And I really do recommend, just to kind of keep things straight in your mind, writing this in the standard order, right? So when you're writing a polynomial, we usually write the highest powers first. That's going to help you keep track of which thing is A and which thing is B and which thing is C if there's a C. So we've got A of X equal to negative 6X squared plus 18X. Great. So now we want to find the X coordinate. We're always going to find the first coordinate of the vertex. We might find the second coordinate, but definitely the first. So we're going to find V sub X, and that's going to be negative B, which is 18 over 2 times A, which is negative 6. So we're getting negative 18 over negative 12. We should definitely reduce that fraction. We can divide the top and bottom both by 6 and get positive 3 over 2. Because I cancel for negative signs. Or if you prefer, 1.5. I don't prefer 1.5, but if you prefer, that's totally fine. So there's our x coordinate of the vertex. Here's what I would say about these optimization problems. After you have found the x coordinate of the vertex is a good time to go back and read what the question is asking for. Let's go back and read what the question is asking for. Find the dimensions of the largest rectangle by area in the first quadrant that can be inscribed under the line y equals 18 minus 6. So they said find the dimensions. I have found one of them. We have found that x is equal to 3/2. But I need to find the other dimension. So I need to find, I've got the base of the rectangle. I need to find the height of the rectangle. So the height of the rectangle is y. So I need to find y. The easiest way to do that is to go back and look at your constraint. So typically, if you're trying to find the other dimension, you want to go back and look for what your constraint is, because the other constraint usually is your other dimension written in terms of the one you just found. So we just found x, and over here for our constraint, oh, look, there is y equal to 18 minus 6x. So our y dimension is going to be 18 minus 6 times 3/2, which is going to be 18 minus, let's see, 6 divided by 2 is 3, and then 3 times 3 is 9, and 18 minus 9 is 9. So we get y equal to 9. I should point out, because I should, it is not a coincidence that the x value is half of the x-intercept and the y value is half of the y-intercept. That is a pretty standard result for a question like this. So when you have questions like this on your homework assignment, it is most likely going to be that, like, if your thing intercepts, at some y value here and some x value here, the coordinates are probably both going to be half of it. That doesn't mean you can't do the work. You need to still show the work so I can see the two inputs going on. But that is the result you should expect. What would I be finding if I did find the y coordinate of the vertex? Good question. Let's go ahead and find it over here. Over here, sure. I got room. Maybe, sure. Always that. So this is why I don't want to write it as v sub y. I've already used the y variable, and my parabola isn't y equals negative 6x squared plus 18x. It's a of x equals negative 6x squared plus 18x. So I'm going to find the second coordinate, or the y coordinate of the vertex. I'm going to call it the a coordinate, or the function name coordinate. So if I find the other coordinate of the vertex, let's see what we get. So if I plug in 3/2. So here's a good tip. If you do have to plug this back into the original function, it might be easier to plug it into the already factored form. I don't really want to square 3/2 and multiply it by -6 and then do this. I think it's going to be a little nicer if I do it up here. So let's see. If I plug in 3/2 there, I get 3/2 times 18 minus 6 times 3/2. Oh, look at this. That's going to be 3/2 times, let's see, 6 times 3/2 is 18/2, which is 9. 18 minus 9 is 9. Well, wouldn't you look at that? That's just x times y, which is going to be 27 over 2, which is my area. So when I should say not just my area, my maximum area. So this is the maximum area. I know we were not asked to find this, but I just wanted to point out that that is what you would get if you did find it. I'll reiterate. If you find the second coordinate of the vertex, like we just did, you're typically finding the either maximum or minimum value of the thing you were trying to maximize. In this case, we found that the maximum area was 27 over 2, which shouldn't be surprising in that those are the dimensions that maximize the area. If you multiply those two dimensions together, you exactly get 27 over 2. Okay. Okay, we got plenty of time. We got 11 minutes. Great. There's lots of examples. Of all the examples we've done, though, this is probably the one that'll come up over and over and over again in the future. So what point on the line y equals 3x plus 1 lies closest to the point 2, 0? It is usually not something that can just be guessed, unfortunately. That's what it was. So let's try and draw it. And I do want to do, oh, where did I put my ruler? had a ruler. It was like a tiny little ruler. I'm really excited about it. No. I've lost it. Oh wait. Oh, here it is. Yeah. Cool. Awesome. So I want to try and draw this one slightly nicer than I would normally draw. Okay, so let's draw a picture. Not usually so precise, but it's going to be precise sometimes. And I'm trying to draw the line y equals 3x plus 1. Oh, let's see here. So let's use these things. Sure. We can mark this off. 1, 2, 3. Sure, why not? You don't usually have to be this precise. I'm just trying to make it look nice for you all. Okay. So the line y equals 3x plus 1 has a y-intercept of 1. An x-intercept of, well, if y is 0, x is going to be -1 divided by 3. So my line's going to look, you can see it's about right there. Sure. About like that. So I'm trying to find the point on that line that is closest to 2, 0. And from experience, I know it's about right there. Let's zoom in. So the question we're asking, is what point on the line lies closest to the point 2, 0. The question we're going to actually answer is what point on the line will minimize the distance to this other point. So we're trying to find, oh, this pen is trash, sorry. We're trying to find the point, you see that? On the line, y equal to 3x plus 1, that minimizes the distance between that point and the point 2, 0. Whenever you're trying to find a point that is closest to another point, you're always trying to minimize the distance between those 2 points. I don't know what this point is over here, right? We're trying to find it. So I'm going to call it the typical, this pen, I keep trying to use this pen and it's trash. We're going to call it the typical name for a point that we don't know. We're going to call it x, y. So this point over here, x, y. And 2, 0. Okay, so we want to minimize the distance between those 2 points. So we want to minimize the distance, which is equal to the square root of, I do recommend subtracting in the order where your variables are first. Meaning you could do 2 minus x squared plus 0 minus y squared, but I would strongly encourage you to write x minus 2 squared plus y minus 0 squared. Okay. And just like before, the thing we want to minimize or maximize has 2 different variables in it. I don't love that. So I'm going to use my constraint. And the constraint here is the fact that that point has to be on the line. So our constraint is that the point x, y is on the line y equal to 3x plus 1, which means we can substitute in y equal to 3x plus 1 for y. So let's rewrite the thing we want to minimize. Now we're trying to minimize the distance equals the square root of x minus 2 squared plus 3x plus 1. I'm not going to write the minus 0 because 3x plus 1 minus 0 is 3x plus 1. So here is an important thing to know. This will be true whenever you're minimizing distance. That doesn't look like a parabola. I got a square root, which parabolas don't have. So here's the thing that's nice about this. If you're trying to minimize the distance between 2 points, you can minimize the square of the distance. If I make the inside stuff as small as possible, that'll make the square root of that as small as possible. And because the square root function is a function that gets smaller when the input gets smaller and bigger when, right? In fact, I always attempted to write on the board, but I forget that people don't do. So I will just remind you that the square root function looks like that. So if I make the insides of the square root as small as possible, I will make the output, right? If I make this as small as possible, the corresponding output will be as small as possible. Right? If I move further to the left, the y values are smaller and smaller. So here's what we can always say. Instead of minimizing the distance, we minimize. I like to just say the insides, but people usually say we minimize the square of the distance, which is just the insides. And this is, I really, really want to say this because it does come up a lot in other classes. It's always true. If you were trying to minimize the distance between two things, you can minimize the square of the distance instead, which is almost always going to be easy. Right? I don't want to deal with that square root, especially if you're trying to do it with calculus and using derivatives. You still don't want to deal with that square root. It's going to be terrible. So this is much nicer. So we're trying to minimize that. So now I'm going to try and make this look like my usual kind of parabola equation. I'm going to multiply things out. So we have the distance squared is equal to, let's see, this multiplied out is x squared minus 4x plus 4. And this multiplied out is going to be 9x squared plus 6x plus 1. And then if I simplify that a little bit, I get distance squared equal to, let's see, x squared plus 9x squared is 10x squared. Negative 4x plus 6x is 2x. 4 plus 1 is 5. So there's my A, B, and the x coordinate of my vertex is negative b over 2a, negative 2 over 2 times 10, which is negative 1/10. All right, I've gotten to the point in the problem where I've done all the amount of work I should do before I read the question again. Right? After you find the first coordinate of the vertex, go back and read the question. So the question says, what point on the line is closest to the point 2, 0? Okay, so here's what we have. We have the x coordinate of that point. We know that whatever x and y coordinate this point gives us, that distance will be minimized. They didn't ask us to find the minimum distance. They just asked us to find the point on the line. So if I know that the x point is negative 1/10, I want to find the y point. Well, I'm going to look back at my constraint to tell me, oh, y equals 3 times x plus 1. So the y coordinate is going to be 3 times negative 1/10 plus 1. That's going to be negative 3/10 plus 10/10, which is going to be 7/10. So the coordinate that is closest to that point is negative 1/10, comma, positive 7/10 is the point on the line. I mean, if you were doing this question, you could just like find the point and circle it or box it. Like, you don't have to write all these words, and that's right, but I'm trying to do a little more. This point is the point on the line, y equal to 3x plus 1, closest to the point 2, 0. Last thing I'll say here, probably, is that if you found the y coordinate of the vertex, which we didn't find, but if we did, you would be finding what that minimum distance between those 2 points was. Actually, you wouldn't. You'd be finding what the square of that minimum distance was. So if you plug negative 1/10 back into this parabola equation, you would get whatever the minimum distance squared was. And then if you take the square root of that, you can find the mean. But no one asked us to do that. So I would really encourage you to not do more work than you have to do for these optimization problems, right? Don't answer questions that you don't have to answer. It's not like wrong to do that. It's just you don't have to do it. So that's what I'll leave you with. We'll talk more about optimization on Friday. So if this seemed a little bit out there to you, you're going to see it again on Friday. We'll have another chance to revisit it. You can think about what sorts of questions you might have.